should have been double arrow actually. Okay, this should have been double arrow. So indicate that there will be equilibrium between two. If that is the case, so this should have been double arrow. Okay. So forward reaction will be Cl2 forward. The reaction rate will be equal to backward reaction rate, which means K negative 1 Cl concentration power. So I know the Cl concentration will be equal to K1 over K minus 1 Cl2 inside of square root. So plug this guy over here, which means K1 K minus 1 square root, and also Cl2 1 over half. So my overall reaction rate now, if I just plug everything together, this guy together, I'm going to call again K, and the Cl2, CH3. So both of them are my reactant. Anything else? Otherwise, we're going to move on to this part. So on Tuesday we just covered five basic nuclear reaction, right? That was alpha decay, beta decay, gamma decay, and also particle emission, and the last one is electron capture. And we need to know when this guy happened, right? So nuclei, all those elements in nature, they are very stable, but some of isotopes are not stable because their neutron to proton ratio is not proper. So this graph will show, for example, if I have atomic number 10, which means neon. Neon has 10 proton, and if neon has same number of neutron, 10, this is going to be stable. So that same ratio is like a 10 proton and 10 neutron right here. That's stable. And the neon's isotope, like a proton 10, neutron 11, that will be in this location one level higher right here. That is still stable. So when we find out each element and then what ratio make it stable, this will make a belt of stability. Okay. So for example, this element, what is it? So something 53 something. Okay. So with that proton number of proton, if it has this many neutron, this guy is not nuclear active. It's just stable. But if you have more than so if you have too many neutron, for given number of proton that go above the belt, then it's not stable. Nuclear decay will happen. The question is, which nuclear reaction should happen? Because you have too much neutron, compared to proton, this reaction should happen. Okay? One of the neutron should convert to the proton. Now, which of 5 reactions will make that happen? It will be beta decay. Why? beta decay is it emit electron, right? So neutron, which means 0, 1, proton is 1, 1, and the electron is negative 1, 0. So you see that this beta decay will make it this reaction possible. And then if element is above belt of stability, you lose one neutron and increase proton. So it goes one down here, at the same time you move to here, right? So it goes to the stability belt. So in the end, when you have certain element, nuclei, if that is over belt, you can say beta reaction will happen, beta decay. What if your isotope is below belt? That means you have too little neutron. You have too much proton, so reaction should convert proton to neutron. What electron decay, which reaction will make this possible? Electron capture? Yeah, electron capture. Because electron capture will make it, so electron capture to proton, make it 1 here, 0 here. So electron capture will make it 1 less proton, 1 more neutron. If somebody show 1 less proton and 1 more neutron, so it will make it closer to belt. If that's not enough, you're going to do 1 more electron capture to get into the inside the belt. So this is electron capture. But also another possibility is positron emission. So this guy emit positron, and it will also neutron. Why? If they add up together, it match. So if some guy has less neutron, then either electron capture or positron emission will do it. But the thing is, although those are possible, in general, if an element is a lighter element, they will do positron emission. If it's heavier one, if it's still below belt, then it will be electron capture. Okay? It's not 100% accurate, but that's a trend. What if isotope is beyond the atomic number 80, more precisely greater than 83, then this guy has too much nucleon, too much neutron proton together. It's too much. So it's not stable. So therefore, the goal is, before they do any of these reactions, either beta electron capture or positron emission, they want to lose most of mass. Most effective way is alpha decay. Because alpha decay, you can just lose 4 nucleon, including 2 proton, right? So they will continue alpha decay until they enter in this region. And they enter this region. If they enter below belt, now they'll start either electron capture or positron emission. If they enter, so they lose mass and they enter in the above the belt, they will now be in beta decay. Okay? So this is a summary of what I said, and then a little more here. If a nuclei atomic number is less than 20, then the stable ratio will be 1, which means if an atomic number is less than 20, this just 1-to-1 ratio is the best ideal ratio. So you can look at periodic table. Carbon has 6 proton, 6 neutron. Nitrogen has 7 proton, 7 neutron. Oxygen has 8 proton, 8 neutron. So up to atomic number 20, their ratio will be almost the same. Okay? It's 1-to-1 ratio, that will be ideal. If there's a little bit off, 1 more, 1 less, it's acceptable. Okay? ratio 1 is stable ratio for any element below 20. Okay. But beyond that, the ratio increase, which means, as you can see, after atomic number 20, this slope is just more than 1. The slope is increased. So end of the graph, which means atomic number 80, this ratio approach 1.5. So that means if you have a proton 80, you need a neutron 120, make it stable nucleus. Okay? So neutron work as a glue. Because proton has positive charge, they do not come together. You need to use glue, so that's a neutron. So you need more of a neutron, then you have a lot more proton. So what if that atomic number go beyond 80? This ratio increase up to 1.6. But it doesn't matter how many neutrons you have. If once atomic number increase more than 83, it's just unstable. Okay? No matter what ratio you have, it's not stable at all. Above belt, there will be beta emission. Below belt, there will be a partial emission or electron capture. Yeah, this is what all I said already. There is a certain number that make a nucleus stable. For example, if a nucleus has proton as this number, this guy have extra stability. So for example, 82, atomic number 80 is red. Red has, no, not red. Is it red? No, I don't think so. Where's red? Yeah. Is it right? 82? Okay. So red is very stable compared to other element. So most uranium, nuclear, radioactive element, they will decay until they become red. Okay, because this is stable. When you say stable, that means as long as you have number of protons 82, you can have many different number of neutrons, because this is stable. Whether N has more or less, then you have a wide range of stability. Let's go back to this guy. 82, we don't have it here, but it's a little bit wide, and then you can have multiple isotopes possible. And then number 50, if you look at here, do you see that it's filling almost all the belt here? This is tin. And tin is also very stable, so you can have very many different kind of different number of neutron. So this guy is known as, it has most isotope. I think there are about 10 different isotopes. So those are the magic number. So if you have that many number of protons, that element is not element, nuclei is stable. Nuclear stable. And also for neutron, if you have, it's all the same number, right? Same number. There's one more, 126. If neutron is this number, that's also extra stable. So another thing is either proton or neutron, if they have even number, that's more stable, more likely stable than having an odd number. So if you, in the nature, that we have, when both proton number neutrons are even, we have 157 stable isotope. On the other hand, there are only 5 isotopes are stable with odd number. Okay? So somehow they want to have a pair. So when they come to nucleus, somehow they like to be together with other pair, so then they get even number. Same goes with the electron. Electron also prefer to be paired with the other electron. So why don't you try to do some practice here? So at what atomic number this ratio make it unstable nuclei? If you look at the most element, most nuclei, 1-to-1 ratio is good for stability. But when the atomic number increase, there's some point this is not a good number. 21. Up to 20, this ratio is ideal. But from 21, if that's 1-to-1 ratio, it's not stable. So 21. Okay. Which isotope will be most stable? When we say stable, they don't show nuclear radioactivity. Okay. So it doesn't decay. Which one do you think is most stable? Red? Because because you said red. Okay, yeah, because you mentioned the matching number. That's right. But if you don't know about the matching number, you have to do some calculation. Let's say this oxygen has proton number 8, neutron number 9. Right? So ratio N over P is 1.9 divided by 8, 1.125. So this is 12, around 12.5% off from ideal ratio, right? This guy, 6 proton, 8 neutron. So ratio is 1.33. So still number is less than 20. So 1-to-1 ratio is ideal. That means 33% off from ideal ratio. This guy, one proton, 2 neutron. %% off. Right? Very bad. This guy, even without thinking about ratio, atomic number is greater than 83. So it is just unstable. This guy, pretend this was not red. For example, it read 81 and that's different number. Then you have to calculate ratio, right? So in this case, it was a matching number. But proton 82, neutron 1-to-6. So that ratio is 1-to-6 divided by 82, 1.54. Now this number is very high. If you look at the graph, it's beyond the graph. So that's when stable ratio is actually 1.6, right? This is stable ratio. So I can see that is this is off by 0.06. So okay, I can do. Okay, it's supposed to be 1.6 ratio. So this is 1.54. 1.54 divided by 1.6, 96, which is 4% off from the ideal ratio. So from the number, I can see 12% off, 33%, 100%, 4%. So this will be most stable. Okay.
Real quick, how did you know that that one was most stable at 1.6? That ratio?
Because when atomic number is less than 20, ideal ratio is a one-to-one ratio.
Mm-hmm.
But after that, it goes up. The ratio increase from 1.1, ratio 1 to 1.5. The 1.5
okay, I
is
see
when
it.
you are
Thanks.
80. But that element is 82. So it goes up to 1.6. Okay? That's why I say 1.6.
So you just knew it was 1.6? Or you knew it was greater than 1.5?
Because you memorize 1.6 is
Okay.
stable ratio when higher atomic number.
Okay, thank you.
But it doesn't have to be 1.8, 1.9 because at that point it's too heavy, it's unstable anyway.
Okay.
So the 1.6 is the kind of maximum ratio that makes it stable. What will happen to carbon 11, C11? What will happen? What reaction will happen? So C11 is atomic number 6, mass number 11. That means we have 6 proton, 5 neutron. So what should happen? Alpha decay? So atomic number less than 20, then we ideal situation have same ratio. Okay. Yeah. So this guy has a lacking neutron. So you wanna make it more neutron, right? So that means proton should turn into neutron. Or you could just say, because this is N to the P ratio is less than 1, that's below belt. If it's below belt, even without thinking too much like an algebra stuff, from the graph, you just remember that below belt, either electron capture or partial emission. One of them will be answer. Okay? Just in case, in multiple choice, if you see both electron capture and partial emission, then you have to choose one. Most time, they would not show both of them at the same time. Okay? But what if they show it? Well, then lighter nuclei prefer partial emission under the belt, and the heavier nuclei under the belt prefer electron capture. Okay? So this guy is positron emission more likely, but if you say electron capture, that is also accepting. Because it's not 100% clear cut one or the other. Okay? So both are good answer. Okay? Now, which element do you think is the least stable? I don't see matching numbers, so you have to do a little bit of math. Right? I don't see any matching number. Least stable. Even if you have matching number, that's not an answer because we are looking for least stable. Alright. Calcium, what's the atomic number for calcium? 20? So calcium 40 will be then you have 20 neutron. So N to P ratio is now 1. And the atomic number is still under 20 or up to 20. So this is good, right? This is stable. Ratio 1 is good, stable. Oxygen, P is 8. Is that 8? No. 8, right? 8. And N is also 8. Ratio is 1, which means stable. Phosphorus. What's the atomic number of phosphorus? Is that 15? 15, okay. Proton number is 15. then make it neutron number as 16. So 16 over 15 is 1 point something. 16 over 15 is 1.07. Okay, 1.07. Because our timing number is less than 20, the ideal ratio is 1. Then make this guy is 7% off from ideal. 7% off from ideal ratio. Okay. Zinc. Zinc is my eyesight is it 30?
Yeah.
Okay, 30. So zinc, wow. Number of protons is 30. Number of neutron is 6. We have a winner here, right? So if that atomic number is more than 20, ratio should increase from the 1, right? But this guy is complete opposite, very small. So I think this guy is supposed to be winner. 6 over 30 is 0.2. So ideal ratio for this guy might be 1 point something, but it's 0.2. I think this is really bad. So let's see what silver does. Silver atomic number is the 47. Okay, 47. Then making number of neutron is 61. So 61 divided by 47 is 61 divided by 47 is 61 divided by 47 is 1 point about 3. But this guy is 47, which means ratio can be more than 1. 1 point. So we don't know because you cannot memorize this graph, right? But what we know is it will be greater than 1 or less than 1.6 because it's in between somewhere. So maybe 1.3 or 1.2, 1.4. So if it's 1.3, this is really ideal. So it seems like very close to ideal, but we don't know exactly, right? But when we look at compare this guy, this is really bad. 0.2 is really off. So we know that this guy will be least stable. What will be the next least stable one then? This guy is a winner. Which one do you think is next least stable one?
Phosphorus.
Probably phosphorus. But until we actually know where this guy actually locate, we cannot say for sure. But probably phosphorus, but we are not sure. Okay? Because why don't we go silver actually? Silver number was again 47. 47 is right here. So if I move 47, it's here. And the 47 Newton 61. 61 is here. So seems like this guy is stable. Okay? So probably answer is phosphorus. But most time you may not give this graph, so they wouldn't ask that kind of question. Okay? Although that's the principle. They may not ask you between phosphorus, silver, which is more stable. They would not ask you. Okay? They will give you like one very old, isotope. All right. So once you have like a very heavy isotope radioactive one, that guy is too heavy, then you start alpha decay. So in the my x-axis is number of proton, or you can say atomic number. Y-axis is mass number, not just number of proton, not number of neutron, it will be mass number. So number of proton plus number of neutron. Because uranium is too heavy, they're gonna start alpha decay. So alpha decay means you lose 2 of proton, 4 of mass number. So you move in x-axis 2 down, and y-axis 4 down. So this guy become 2. Okay? And then they may continue the alpha decay to reach to lead. But sometimes they may mix alpha decay with beta decay. If beta decay happens, that means you are emitting electron. If you emit electron, mass number doesn't change, but by emitting electron, your number of proton increase by 1, right? So it moves 1 step into x-axis. And then at some point, if you move up here, because atomic number increase, that is very become unstable, and then start alpha decay again. Okay? So we don't have to know all the detail process of decay, but you just recognize, oh, there will be alpha decay, this should be beta decay. That will be enough. Eventually, if they end up become red have magic number, it's very stable, so that is stable. But when you say stable, it doesn't mean it will stop there until, so this guy still again continue beta decay, making higher atomic number, which cause another alpha decay. So they continue beta and alpha decay until make real stable red isotope. Okay? So we did like 5 basic nuclear reaction, and there's other case. Nuclear reaction will involve that you use alpha particle and bombard other nucleus, then make it that initiate nuclear reaction. That is what we call nuclear transmutation. So difference between this base decay and that is, this guy you don't have to use any alpha particle or other stuff. So you do not shoot any particle to nucleus. This is a kind of just decay, right? It's in some sense this is the first order reaction. This is second order reaction. Why? It involves 2 of the particle, but this one is just you have 1 particle and decay into other. So that's the difference. But here we call, instead of second order reaction, we just say nuclear transmutation. It's just about terminology. Other than that, we just use same algebra to match left side, right side, have same mass, total mass number, and total atomic number. That's all. But the thing is, to make the transmutation happen, you have to accelerate your alpha particle. Why? Alpha particle has positive charge. And then we are showing this guy to nucleus. Nucleus has another positive charge. So because they have the same charge, they do not come together. To make that happen, you have to accelerate this guy at high speed. So we need a special instrument that we call a cyclotron or synchrotron. So we have one of those very good facilities at MSU. That's why MSU is very known for particle physics. So that can be used for nuclear transmutation. This is just very simple diagram how cyclone works. Cyclone will have a huge magnet on the top, so you can say just a sheet of layer of magnet on the top and the bottom. And you can say one of them has north side of magnet, the other is south side of the magnet. Then there will be a magnetic field between top and bottom. Okay? So when you have magnetic field, doesn't matter, the direction doesn't matter, but and then you shoot any charged particle like a helium, no, not helium, alpha particle. So that will partially charged. Then what happens is the moment it enters this magnetic field, it stops circular motion. Okay, so that is from physics law. So once they enter in between this magnetic layer, it just stops circular motion. And then the circular motion has constant radius. It just keep orbiting in same circle. But what we want is we want to accelerate the particles, which means when you just string a stone with a string, you want to increase speed, so you have to make it accelerate. To do that, you have like a two chamber, like we call it D. So it may make an orbital circular motion here, but anytime it across one D to the other, they apply electric field. So magnetic field between top and bottom make circular motion. Now electric field between this D make whenever this guy cross one from one D to the other D, it accelerates. So each time whenever it's rotate, like a circular motion, it just increase radius and then make it faster. So eventually when they escape this D, it have huge velocity. That's how it accelerates charged particle. And then they will be used to react with other molecules. Now, if we use neutron, so let's say we have a nucleus, any nucleus, and if you use an alpha particle, because they both have plus charge, we need to use a cyclotron to accelerate this particle. Otherwise, they would not come together, right? But instead of any charged particle, if you just use neutron does not have any charge. So there's no resistance from the opposing nucleus, right? Because it's neutral, this guy will allow neutron to approach to very close. So if you use neutron, you don't have to use really high energy accelerator. Okay? That's the advantage of using neutron. And that neutron is nowadays used to cure cancer. So traditional approach using radiation is they use a charged particle, but nowadays they just replacing that with not replacing. They are using a neutron, and that's more effective, like 7 or 8 times more effective. So cancer is a little more curable now. Okay, they're going to use more neutron in that treatment. This is an example of transmutation when you use alpha particle compared to using a neutron. But there's nothing special. Just when you add a number, you just match left side to the right side and just predict one of those missing pieces. They may show you some box showing a blank of a certain element, certain nucleus, that you should have to predict which one should be there. We just talked about there will be a nucleus decay, alpha decay, beta decay. So there are many different kinds of decay. This decay actually follows first order reaction. So as you did in the chemical kinetics, zeroth order, first or secondary order reaction, that first order reaction just apply exactly the same way to nuclear decay. Only difference is nuclear half-life is not affected by temperature. Now let's think about this in terms of chemical kinetics. Half-life, the first order was ln2 over k, and k was in terms of Arrhenius equation, it was this. Therefore, if you change temperature, you change k. If you change k, half-life change. But this is true for chemical reaction only. And the nuclear decay, this half-life, although the equation is same, this is not dependent on the temperature. Okay? So that's why this is reliable dating of old day. So in the ancient time, like really ancient time when you have dinosaur, temperature might have been a lot higher than now. They would not affect half-life of any element. So we can trust, we can assume half-life can be used to predict those age of fossil. Okay? If that was chemical reaction, you cannot use that approach. Because this nuclear reaction, we can use it. Okay? And also, another reason is so this is why we use this carbon dating for predicting age of fossil or artifact. Okay? So this is how we use carbon dating or radiometric dating. Life form on Earth is carbon-based. Right? We don't know that in other life in other planet has some kind of different element as based, but any life in Earth is carbon-based. So because of that, we know the stable carbon is carbon-12. But we also have some carbon isotope that's carbon-14. Now carbon-14 is radioactive, which means this will decay. So if you have carbon-12 in the nature, that will stay as constant number. But carbon-14 will decay. If you have a certain amount, over time that amount will decrease. But the thing is, cosmic ray will always convert nitrogen-14 to carbon-14 by cosmic ray. Because of that, although our carbon-14 will be unstable and decay and decrease, that amount will be replenished by cosmic ray. So the ratio of carbon-12 of carbon-14 in the air in the nature will stay constant. Okay? So that means if a plant use carbon-based, which means plant need to absorb CO2 and H2 for their survival, right? That's how they make a glucose, energy source. So they use carbon from CO2. This C has, sometimes they use carbon-12, sometimes they use carbon-14 because it's all mixed up. So that ratio will be same. So plant, if you just investigate plant, their ratio of carbon will be same. And the herbivore eat that plant, so composition of carbon in herbivore will be same as the ratio. Human and carnivore eat those herbivore and plant. So our composition of carbon was the same as between C12 and C14. So we may lose some carbon-14 due to radio decay, but we keep eating new food every day. So our ratio, the ratio between 12 and 14 will still stay same, okay? Until we die. The moment any life form die, that's when they are not able to eat any more new food. They cannot breathe. Plants die, then they cannot do any more activity, right? That moment, C14 you amount C14 will decay, C12 will stay. Right? So this ratio go down. That's how you're gonna determine age of fuel, fossil fuel, fossil or alcohol. So with that principle, we just use same intermediate law that we use for first order reaction, because anytime then you have half-life and then some decay, that will be first order. The only difference is when we use this law for chemical reaction, that was concentration of surface space at the initial moment, concentration of that one at time later. Instead of concentration, we use amount of nuclei. It's the same formula, just initial amount of nuclei, later amount of nuclei. Everything is same. So half-life also same equation. So whatever you learned at chemical kinetics, just apply to nuclear decay as well. So this was this will remind of one of the questions you have in the quiz. Half-life of sulfur is this. How long will it take 90% of sample of sulfur disappear? Formula was N0 NP minus KT. And if 90% disappear, that means 10% will remain. If 10% will remain, number here will be 0.1. Why? Because originally you had 100%, now you have only 10% remain. The ratio is 0.1. I need KT. We are given half-life. Half-life is 86.7 days. So I know the K value will be ln2 over half-life. So ln2 over 86.7 days. Because I know K, this number can go right here. And I can solve for time. So time will be ln 0.1 divided by this number K. How do I calculate? ln2 divided by 86.7 0.00799. So that's my 0.00799. And then we have a negative sign here. So negative goes here. And if you do calculation, 288 days. 288 days.
I'm sorry, how did you get from, how did you get 288 days?
Why don't I type actually? Negative logarithm 0.1 divided by.
Oh, okay. So you just did the division in it. Okay.
Yeah.
Never mind, I'm good.
Next question is similar to first one, so I want you to do as your practice. Now, what about this guy? Why don't you try this one? This is a little different from chemical kinetics. It's almost same, but it will be difficult to recognize it. A little bit difficult. In terms of calculation, actually nothing different from chemical kinetic, but recognizing is challenging, I think. Do you see how you can do this one? Seems like you have some idea. So as long as you recognize that, so this is not concentration or anything. This is a decay rate, right? Rate is proportional to amount of reactant. So I'm using just rate law from the chemical kinetics. And it's first order. So you have first order here. And they are giving us decay rate. So I'm just using that decay rate. But initial decay rate, when material is still alive, it's faster. But once it's dead, because you have less amount remaining, the decay rate goes slower. So from this ratio, I can find the ratio of this guy. That is the ratio we need in the equation. So I can put that number down here, and then solve for time. And the K value is coming from half-life. Okay? That's how you can approach. We have just only three slides left. Okay. No more math. Just. Oh, do you need this one? Alright. So we all know that radioactive material is dangerous. So we need to know how to detect the radiation. We have a couple of devices. The worker who work at the nuclear plant, they have a carry badge on clothes. Those badge has some kind of gas chamber inside of it. So if radiation hit the badge, it will create some fog inside the badge. So that's why they call badge dosimeter. Now Geiger counter is the device has argon gas inside of it. So if radiation hit argon gas, it ionizes it. So argon is a neutral, but it will become ion. So it will carry electricity. So device catch that electric current and it will show from the device. Okay, that's Geiger counter. We just need to know that how that works. That batch dosimeter use how much fog it produces. Geiger counter is how much electric current will be produced from radiation. For scintillator counter, it uses phosphorus. The property of phosphorus is if that interact with radiation, it will show light. Okay, you know that in the nature, like what firefly? Firefly has like a light, right? You'll use something like a phosphor, similar principle. Now, radio tracer is useful to identify mechanism, how reaction happens. For example, plants use water and carbon dioxide to produce glucose. This is a food for everybody, right? Now, question is, another product will be oxygen. Now, is this oxygen coming from CO2 or water? How do you know? Because we may know answer now, but in the past maybe we didn't know. So what we could do is regular oxygen is oxygen 16. So instead of oxygen 16, we use oxygen 18, which means radioactive. Okay. So if we will label either this one or that one, just exclusively as radioactive oxygen, then we will know where this guy go, right? So you either label CO2 or H2O. As a result, you will know this guy. This oxygen always go to oxygen gas. So this oxygen can go either glucose or oxygen. So this is possible when you use radio tracer. Okay. So not much. That's just like how we use radioactivity.